All right, so good morning, everybody. This is February 22nd, Math 0310. Some WebAssign due dates that you should be aware of. 868788, that's one assignment that's due, and I have extended that one day. So that's due the 26th of February. And then 919293 is one assignment. That's due on the 4th of March. And so is section 94. That's also due on the 4th of March. That's the end of next week. So it's hard to believe that we're already heading into March, that we're getting very quickly getting towards that month. So today we will be continuing talking about square roots. We're going to talk about multiplying square root expressions together and dividing square root expressions. And then we will also, when we talk about dividing, we'll talk about what rationalizing a denominator means and how to go about rationalizing square roots in denominators. So let's talk about square roots. I'm going to go to the next screen and kind of look at an overview of what we've done so far. Right? So first of all, we've just talked about evaluating. So like if you have the square root of 81, right, we know that that's the positive or the principal square root of 81. It's the positive number that you square to get 81, and so square root of 81 is 9. So remember, when you have the square root of 81 written as a radical like that, you replace it with the number 9. Those mean the same thing. Square root of 36 is equal to 6. Square root of 144 is equal to 12. And then don't forget also what we talked about last time, that the square root of, let's say, negative 25, remember when you take the square root of a negative number, that right now we're simply going to say that that's not real, right? Not a real number. So that's evaluating square roots. And then we've also talked about variable expressions. So if x is positive or 0, remember we've talked about that the square root of x squared is x. And the square root of x to the 4th is x squared. And the square root of x to the 30th is x to the 15th. That's a 30 right there. Kind of didn't exactly look like that, so let me rewrite that one. So the square root of x to the 30th is x to the 15th. Remember, the idea here is that when you're taking square roots, you divide the power by 2, which happens to be the root that you're talking about, right? You're talking about the second root. And that's not a coincidence. We'll talk about that more later. But you divide the power by 2. All right, so we talked about evaluating square roots, whether they were constants or variables. And then we talked about simplifying square roots. So simplifying a square root would be if you had the square root of a number, right, that was not a perfect square, like 18, right? We talked about the idea that you could rewrite that as the square root of 9 times the square root of 2, and then rewrite that as 3 times the square root of 2. And the idea was to take the number underneath the square root and make it as small as you could. And remember that you also want to use the biggest number, and you want one of the numbers to be a perfect square, right? So square root of 80, you would not break up as the square root of 8 and the square root of 10, right? Because neither is a perfect square, right? Neither factor is a perfect square. That's not what you want, right? So no, don't do that, right? So I'm going to put no on that one. But what do we want to do? We want to take square root of 80 and rewrite it as the square root of 16 times the square root of 5. 16 is a perfect square, right? And so you want, remember, that's a key idea there to simplifying, is you want one of the factors to be a perfect square. And so then you could write that as 4 times the square root of 5. So we talked about simplifying. And then we also did this with variable quantities. So for example, the square root of x cubed. The 3 is not divisible by 2, so we break it up into 2 factors where one of them is divisible by 2. So we break up x cubed as x squared and x. And then we'd rewrite that as x times the square root of x. Excuse me. And so you would do that with any odd power. So the square root of x to the 19th, you would break that up as the square root of x to the 18th times the square root of x. Right, that's the biggest power that you could get that's divisible by 2. And then the square root of x to the 18th, like we saw just above, you divide the power by 2, that's x to the 9th, and then that would be times the square root of x. So we've talked about simplifying square roots. All right, and then we talked about multiplying square roots. And that you could multiply 2 square roots together, right? So that multiplying, if you had the square root of 3 times the square root of 7, that was the square root of 21. Right? So that with multiplying, it is okay to take 2 square roots and multiply them together. That the square root of a times the square root of b is equal to the square root of a times b. And sometimes it simplifies and sometimes it doesn't after you multiply it. It's like the square root of 3 times the square root of 7 is the square root of 21. Square root of 21 doesn't simplify, so you just leave it like that. But if you had the square root of 6 times the square root of 8, well, that would be the square root of 48. That would be okay to do. But the square root of 48, you would simplify. You don't leave it in that form. Right? You'd write it as the square root of 16 times the square root of 3, or 4 times the square root of 3. But the idea here is that with 2 square roots, it is always legal to multiply them together, right? Now there is one, to be honest with you, we'll talk about it later in the chapter, there is one exception to that rule. Now we have not hit that exception yet, and we won't until the very end of this unit. But there is one exception to that rule that we'll encounter later in the chapter. All right, so with multiplying, it's legal to take 2 square roots and multiply them. And then we've talked about dividing 2 square roots. So, for example, the square root of 75 divided by the square root of 3. that would be legal to divide them. That's the square root of 75 over 3. Or the square root of 25 or 5. Right? That you can take 2 square roots and you can divide them. And so the rule might be written like this. Square root of a divided by the square root of b is equal to the square root of a divided by b. Right? That it's legal to divide 2 square roots. Sometimes, again, it helps. Sometimes, maybe not as much. You know, it just depends on the problem. So the square root of 15 divided by the square root of 3, you could divide the 15 by the 3 and get the square root of 5. Right? But that would be okay to do. And then finally we finished with adding and subtracting. And we saw that adding and subtracting was really different than multiplication and division. Right? That the square root of a plus the square root of b was absolutely positively not equal to the square root of a plus b. And the same with subtraction. Right? That you can't add or subtract 2 square roots. Sandra, go ahead and fire away here. So let's see. Sandra's asking, and what you said is absolutely correct, Sandra. I'm going to mention that. So Sandra's question. Let me finish this little statement here. But Sandra just texted me a question here. So let me move this down a little bit to give a little bit of space here. So her question referred back to division, and that was, would it be okay if you had, and I probably should have put an example in here like this, but would it be okay, for example, if you had the square root of 45, let's see, let me back off on that just a second. Let's say we had the square root of 45 over 16. Would it be legal in a case like that to kind of reverse what I was just talking about and take a division problem that's underneath a radical and separate it out? And that is absolutely the same rule. Absolutely no problem with that at all. So this would be okay, and sometimes it's an advantage to do that, to rewrite that as the square root of 45 over the square root of 16. And then the square root of 16 is 4. And then the square root of 45, you would simplify as the square root of 9 times the square root of 5. And so they give you 3 times the square root of 5 over 4. So absolutely, sometimes it is to your advantage to separate a square root out like that and treat the numerator and the denominator separately. So another example like that, we saw some examples like that in our textbook in section 9.2 of your book. So for example, back in section 9.2, problem number, let's say problem number 130, you have the square root of 72x to the 5th over y to the 6th. Maybe a little bit more complicated, but same deal, that I could separate this out and write this as the square root of 72x to the 5th over the square root of y to the 6th. There's nothing you could do with the fraction. The fraction doesn't simplify at all. And so, you know, your only other recourse there is to separate it out and see if you can do something with the individual radicals. So in this problem, notice what we would do is we would take the square root of y to the 6th and get y cubed in the denominator. And then in the numerator, we would split that one up. Right? The 72 would get split up as 36 and 2. Remember, you're looking for a factor of 72 that's a perfect square, and that's 36. And then you take x to the 5th and break that up, because the 5's not divisible by 2. Remember, when you take the square root of a power like that, of a variable, you divide the power by 2. If it's not divisible by 2, then you try to simplify it. So I could break that up as x to the 4th and x. And so the simplified version of that fraction would be 6x squared times the square root of 2x. Like that. That would be in the numerator, and then in the denominator would be y cubed. So Sandra, hopefully that helps straighten that out for you, and that's okay. Okay, good. All right, so getting back to addition and subtraction, right, the rule is, first of all, that you can't add or subtract 2 square roots. But you can add, right, but you can add if the square roots are what we call like radicals. And remember, like radicals are just simply square roots that are exactly the same square root. So 3 times the square root of 5 plus 10 times the square root of 5, right? Those are like radicals. And so those can be added together. And you get 13 times the square root of 5. All right, so that's a situation where you can add them together. By the way, a WebAssign issue that a student has brought up with me on this section is a problem like this, and this is really not especially good, in my opinion. But let's say you had 8 times the square root of x minus 9 times the square root of x, right, as an example. Those are like radicals. They're both square roots of x. And so you take 8 minus 9 and you get negative 1. Now, if you write negative 1 times the square root of x, WebAssign will count that wrong. So WebAssign counts this wrong, which is not good that they would do that. So WebAssign counts this wrong. And they count this right, just the negative of the square root of x. So WebAssign counts this right. So counts this as correct. Now, there should be no reason why either one of those shouldn't be okay. These are equivalent. There's nothing wrong with either one of those. And it should count both of those as being correct. But it does not take the first one and write it. And I tried it out myself, and absolutely it was counting it incorrect. In fact, it was counting something like this correct. If I wrote just 1 times the square root of 3, it counted that wrong, and it would count the square root of 3 as correct. Right? I even put 1 times. I formally put a square root, a multiplication symbol in it, and it still counted it wrong. Right? WebAssign counts these wrong. And counts this one as correct. Now, once again, they are the same thing. And if you did this on a test, I would be just thrilled if you wrote it either way. So I don't care at all, and it will never matter in future math classes. In your college algebra class, your college algebra professor is not going to care which way you write that at all. So it's not. I'm not really sure what the issue is there, and that's actually a problem I should send in as a correction to WebAssign, because there's absolutely nothing wrong with it. When I send that in to WebAssign, and I've done this, several of you have emailed me saying, hey, there's an issue with this problem, because that's happened once or twice already this semester, and it happened once or twice last semester also. I'll send that off to tech support at WebAssign, and what they do is then they'll run it by people in a math department. They have somebody that they're consulting with, and they'll look at the math. If there's not just a coding error of some type, they'll actually run it by somebody in a math department somewhere to say, hey, is this a legitimate complaint that this person has about this problem? And I would say that this should be a legitimate complaint here, because there should be no reason why it should count those as being incorrect. So, but I wanted to point that out to all of you who are listening live, and also who are going to watch the recorded version of this later. All right, so sorry, my voice is a little bit hoarse this morning. So now in a problem like this, and we were finishing the day last time with these kinds of problems, and I'm not going to go just nuts with this, but I do want you to be able to deal with this situation. These are not like radicals, and so I cannot subtract them. But we can simplify each, and so we do that, and then see what happens from there. So if you can simplify, you do it. So 72, remember, you want to break these up as multiplication problems where one of the factors is a perfect square. And so 72, we just did this one a minute ago, is 36 and 2. And so that's 6 times the square root of 2. And then 98 is 49 and 2. 49 is the perfect square. And so that's 7 times the square root of 2. Right? And this actually is an example of what I just talked about a second ago. So 6, these are like radicals now. And so now we can subtract. And so you get -1 times the square root of 2. Or just the negative of the square root of 2. Either one of those will be very acceptable answers. Like I said, I'm not going to go just absolutely nuts with that kind of problem, just so you know. But I do want you to be able to simplify square roots like that are adding and subtracting problems. And by the way, don't try to force it. And so if they're not all like radicals at the end, then you don't add them together. So as an example, let's say I have 3 times the square root of 18, excuse me, plus 6 times the square root of 12 minus 8 times the square root of 50, like that. All right, so none of those are like radicals. So let's go ahead and simplify each one of them. So you simplify each first. So simplify each square root first. So when I do that, the square root of 18 is 9 and 2, right? That's the factor that's a perfect square. And the square root of 12 would be the square root of 4 and the square root of 3, like that. 4 times 3 is 12. 4 is the perfect square. And then with 50, that'd be the square root of 25 and the square root of 2. Once again, make sure, and I'm trying to emphasize this over and over again, one of the factors has to be a perfect square. And so if there are no factors that are perfect squares, then it does not simplify. So notice in this case, all those factors that I highlighted there are all the perfect square factors. And so this is 3 times the square root of 2, plus 6 times 2 times the square root of 3, minus 8 times 5 times the square root of 2. And so that's 9 times the square root of 2 plus 12 times the square root of 3 minus 40 times the square root of 2. And so notice in this case, the like radicals are the 2 square roots of 2. The square root of 3 is not a like radical. And so all you can do there is combine the 2 like radicals. 9 minus 40 is negative 31. And then the 12 squared of 3 just comes down for the ride. Right? There's nothing else you can do with that. Don't try to force it at the end. Not like radicals, so you can't add them. Right? And so you're stuck with it in that form. All right, so what we've done is gone through kind of an overview again of 9.1, 9.2, and 9.3. And so now we're ready to move on to section 9.4 and talk about multiplying square roots together. So 9.4, multiplication. And I am taking problems out of your textbook from page 1056 and 1057. So if we start off with problem number 252, remember we know that we can take any 2 square roots and multiply them. So problem 252, you have 2 times the square root of 5b cubed, that's in parentheses, times, in parentheses, 4 times the square root of 15b. Like that. See, so that is all multiplication in there, right? It's 2 times that square root of 5b cubed times 4 times the square root of 15b. And that's a 15b, not 156 right there. Right, so this is all multiplication. And so that means you can rearrange those factors in any order you want. And so what do you do here? Well, you put the 2 and the 4 next to each other because you know you can multiply those. And then you put the 2 square roots to get next to each other because you know you can multiply those. So you see, I put the things that I know I can multiply together next to each other when I rearrange that. So 2 times 4 is 8, and the square root of 5b cubed times the square root of 15b would be the square root of 75b to the 4th power. All right. Now simplify that square root at the end. Right, and so we break the square root of 75b to the 4th up into 2 factors because 75 is not a perfect square. So 75 gets broken up as 25 and 3. And then b to the 4th is a power that is divisible by 2. And so the b to the 4th just goes over here with the 25 because that's a perfect square. All right, and so then you get 8 times 5b squared times the square root of 3. And then you could finally finish that as 40b squared times the square root of 3. And that is our final expression there at the end. So again, the idea is that it's okay to multiply 2 square roots together, right? That's legal to do. All right, so let's move on. Let's kind of look at some ramifications to this problem here, that if x is positive, that we know that the square root of x squared is equal to x. So one more general way to write that is you could say that if Bob is positive, or 0, that the square root of Bob squared is equal to Bob, and you might see that written 2 different ways. Notice the first way I write it is with the square underneath the radical, and the second way I might write it is with the square outside the radical, but those mean the same thing. And so either way you get Bob as an answer there. So as an example here, if you have the square root of 3 quantity squared, right, that's equal to 3. Right, when you square a square root like that, technically you could say it's the square root of 3 times the square root of 3. It's easy to verify that this is true if you're worried about it, because that's the square root of 3 times the square root of 3, because that's what the square means. So that'd be the square root of 9, and then what would we get? We'd get 3. Right? So it's a lot easier on you if you just know that that's what's going to happen when you have the square like that. So any positive number underneath the radical, when you square it like that, you're going to get the number that's underneath the radical. So the square root of 15 squared is 15. It doesn't matter how complicated it is. So the square root of, let's say, 10x to the 7th, quantity squared, as long as the x is positive, remember, then that's going to be equal to 10x to the 7th. Right? You always get what's underneath the square root like that. So definitely kind of something to pay attention to there. All right, let's see. This is problem number 262 in your book. Number 262 on page 1056 again. So you have negative 3 times the square root of 12 times negative 2 times the square root of 6. So that refers back to a problem that we did on the last screen, right? This is a place where you, since it's all multiplication, you just rearrange the factors so that the factors that you can multiply together are sitting next to each other, like that. So rewrite that as the negative 3 times negative 2 times the square root of 12 times the square root of 6. And then negative 3 times negative 2 is positive 6. And then the square root of 12 times the square root of 6 is the square root of 72. And then simplify the square root of 72. So that would be, and we've done that, square root of 72 has come up several times today. That's 36 and 2. And so that's 6 times the square root of 2. And finally, that's 12 times the square root of 2. So remember, you're saying that this number right here and this number right here are exactly the same number. If you got a calculator out and started getting decimal approximations, you'd get the same decimal approximation for both of those. Excuse me, my dog is sleeping in the room here, and he's dreaming, so I have to wake him up. So it doesn't make too much noise. All right, so let's move on and look at a different kind of multiplication problem. So we're still talking about multiplication. So this is problem number 264. You have 3 times 4 minus the square root of 3. All right, so this is a little bit different because now we have subtraction involved in the problem. And so the way I'm going to multiply this out is I'm going to use the distributive property. Right, because you've got multiplication across subtraction there. So this is just a classical distributive property problem, right? And so you take 3 times 4 is 12, and then 3 times the square root of 3. Don't multiply those together formally because one's a square root, the other one's not. So you just write that as 3 times the square root of 3, right? You don't do anything beyond that because there's nothing else you can do. All right, that was part A of that problem. Part B of that problem, lots of examples in this page. It's a great page to look at for practice problems. So you have the square root of 2 times 4 minus the square root of 6. So this is exactly the same thing in that this is a multiplication problem across subtraction, like this. And so you use the distributive property. So the square root of 2 times 4, again, one of those is a square root, the other one's not. I can't multiply them together. By the way, do not write that as the square root of 2 times 4 like that, because it gets difficult to know whether the 4 is underneath the square root or not. Very common to see students mess that up. So don't write it that way. It's not wrong, but it's not a good way to write it. Instead, write it as 4 times the square root of 2. That's the preferred way to write it, because now it is very clear that the 4 is not underneath the square root. So I'm going to write this as 4 times the square root of 2, like that, minus, and then we have the square root of 2 times the square root of 6. Can I multiply those together? Yeah, those are both square roots, and I know I can multiply any 2 square roots together. And so that's the square root of 12. And so then we go ahead and do any simplifying we can. The first term, there's nothing I can do, so it's just 4 times the square root of 2. The second term, that's the square root of 4 times the square root of 3. I can simplify that one. And so I get 4 times the square root of 2 minus 2 times the square root of 3. Once again, those are not like radicals. And over and over again on exams, I see students trying to force combining like radicals like this. Or combining radicals that are not like radicals, rather, and enforcing the issue there. There's nothing you can do. Neither of those simplifies in any way, and so there's no way to take those 2 terms and add them together or subtract them. It's just not going to work. All right, so that's problem 264, and so please, I'm going to be working lots of examples here to finish the class up, and so if you have a question about something, you need to stop me as we're going through this. Right now, what I'm doing is all sorts of different examples for multiplication. And gradually, we're going to be looking at different types of examples, okay? Right now, we're just focusing on problems that involve the distributive property and certain things that can come up when you do that. So this is problem number 270, part A, actually. And so you have the square root of 11 times negative 3 plus 4 times the square root of 11. Again, there's addition in there, and so this is going to be a distributive property problem. And you're going to distribute this square root of 11 through like this. And so negative 3 times the square root of 11, that's just negative 3 times the square root of 11. There's nothing I can do to multiply those together. I just leave it as multiplication. And now you have the square root of 11 times the square root of 11 in the next term. So this is 4 times the square root of 11 times the square root of 11. And you can look at that a couple different ways, but that's just the square root of 121, which is 11. See, and that's something I would like you to be able to do, is just notice that when you multiply 2 square roots together that are the same number, that you're just left with the number that's underneath it. That's just another version of that square root of Bob squared equals Bob thing, right? If you have the square root of Bob squared equals Bob, well, that would say the same thing as saying that the square root of Bob times the square root of Bob is equal to Bob. Those are really the same rule, just written in a slightly different way. Right, and remember, this is all predicated on Bob being positive or 0, right? The rule doesn't work exactly if you've got Bob being negative, right? If Bob is positive, that would be true. So I would like you to be able to say, hey, if I'm taking the square root of 7 times the square root of 7, I know that that's just going to give me 7 automatically, right? That would be a good position to be in. That you can do that. All right, so let's look at problem number 274 next. So 274 is a step up now. So you have 8 minus the square root of 2 times 3 plus the square root of 2. And so notice this is an addition problem times the subtraction problem. Still the distributive property. You're still using the same property, but we don't usually organize it quite the same. Here, this looks very much like what we've done with polynomials, in that this would just be a perfect problem for the FOIL method. All right? And remember, the FOIL method is just another way of writing out the distributive property. So when we go through FOIL, you've got 8 times 3 is 24. The outside 2 would be 8 times the square root of 2. Can't multiply those together because one of them is the square root and the other one's not. The inside 2, right, so I've taken the first 2 and multiplied them. I've taken the outside 2 and multiplied them. Now I take the inside 2, so that would be minus 3 times the square root of 2. And then finally the last 2. And notice that's what we were just talking about a minute ago. It's the square root of 2 times the square root of 2. And so that would be 2. It's technically the square root of 4, but that's 2. And then one of those is a positive term and one's a negative term, so that's negative 2. All right, so there's our FOIL method. And now I combine like terms. I've got 2 terms that are like, the 24 and the 2. That gives me a 22. And then the 2 radicals are definitely like radicals. And so I can add those together and get 5 times the square root of 2. And please don't take 22 plus 5 and get 27. Right? That is not what that's equal to. Right? That is going to, that violates order of operations because you're doing addition before you do multiplication there. Right? And so what I like to say to students is if you do that, first of all, you're violating order of ops when you do that. And that when you do that, you are going to go to math hell. Right, that's definitely, violating order of operations is something that always takes you to math hell. And so that's a place I want you to avoid, if at all possible, right? And so 22 plus 5 times the square root of 2, there's absolutely nothing to do to combine those 2 terms. That's what it's equal to, right? It doesn't simplify any further than that. Right, so don't try to force the issue by violating order of operations there. All right, so let's next look at problem number, let's look at 282 next. So 282 is a little bit more complicated version of the last problem. We have 2 times the square root of 7 minus 5 times the square root of 11 times 4 times the square root of 7 plus 9 times the square root of 11. Kind of a yucky looking problem there, certainly. But again, this is another example of using FOIL to do this kind of a problem, right? So you have to be careful here, but if you take your time, you ought to be able to handle this. So you have the first and the outside like that. Now, if you don't want to do some of this in your head, then just write the multiplication out and do that in the next step. You have 2 times the square root of 7 times 4 times the square root of 7, like that, on the first 2. That's okay, and then you can multiply it in the next step. And then the outside 2 would be 2 times the square root of 7 times 9 times the square root of 11. And then the inside 2 would be minus 5 times the square root of 11 times 4 times the square root of 7. And then finally, the last 2 would be minus 5 times the square root of 11 times 9 times the square root of 11. I know it's kind of a hassle to write that out, but if that helps you keep the factors straight as you go through the multiplication, then go for it. Do that. Write it out. There's nothing wrong with that at all. So remember this first multiplication now, the 2 square root of 7 times 4 square root of 7 is just one of those where you do the rearranging. So 2 times 4 is 8. And then the square root of 7 times the square root of 7 is 7, right? That's the square root of Bob times the square root of Bob. Next term, 2 times 9 is 18. And the square root of 7 times the square root of 11 is the square root of 77. The next term, the 5 times the 4 is 20, so you have minus 20 times the square root of 77. And then the last 2 would be 5 times 9 is 45, and then the square root of 11 times the square root of 11 would be 11. That's the square root of Bob times the square root of Bob is Bob again. So take your time when you're doing this, because it's really easy to lose sight of all the factors. So you have 56. The middle 2 radicals are like radicals. So this is minus 2 times the square root of 77. And then finally, 45 times 11 is 450, 495. 495, yuck. Like that. And then you have 56 minus 495, right? Because those are terms that you can go ahead and subtract. Those are like terms. So that gives you negative 439 when you do that. Kind of a big number. And then minus 2 square root of 77. And then there wouldn't be anything else you could do with that. You can't violate order of operations there. And so that would be your final expression there. All right, so a little bit with the FOIL method. So now let's turn our attention to still a different kind of multiplication. This is problem 290. You have 9 minus the square root of 6, quantity squared, like that. 9 minus the square root of 6, quantity squared. And so what I want to refer to here is a pattern. This is distinctly to your advantage for you to know this pattern. We've talked about this a long time ago at the beginning of the semester, but remember, if you have a minus b squared, that multiplies out as a squared minus 2ab plus b squared. And a plus b squared is a squared plus 2ab plus b squared. Right, those two little patterns tell you how to square an addition and how to square a subtraction problem. Right, and what am I doing here? I'm squaring a subtraction problem. So what I would do if I were you is I would, if you know this pattern, it's going to make it easier. What I do is I write out the pattern. And so notice the pattern here is a squared, there's my a squared, minus 2ab plus b squared, like that. But instead of the a's and b's, notice what I did is I wrote out parentheses, little open sets of parentheses there. And then what you're doing is you are just dropping in the a and the b that you've got in the original problem into that pattern. So a 9 goes in the first two terms, because those are both a's, and then the square root of 6 goes in the second two open sets of parentheses, like that. Right? And you've got it multiplied out. Now it's just a matter of doing the arithmetic. Writing out that pattern really will help when you're talking about squaring addition or subtraction problems, especially addition and subtraction problems that have square roots in them, because those can definitely be tricky to do. So then do the arithmetic. 81. And then this would be minus 18 times the square root of 6. 2 times 9 is 18. And then the square root of 6 squared, that's the square root of Bob squared. And so that's just Bob. That's 6. And then add the 81 and the 6, and you get 87. 87 minus 18 times the square root of 6. And then you've got it squared out, right? It really is going to be helpful that if you can go through this kind of a process. Now this was 290 problem A, so we're also going to look at problem B. We have 10 plus 3 times the square root of 7, and that's squared. So it's another problem where you've got the square, in this case the square of an addition problem. So these rules up here are for squaring addition and subtraction problems. And it's super helpful. It is super helpful when the addition or the subtraction problem has a square root in it, at least one square root in it. So in this problem, this is the square of an addition problem. So write out the pattern. And so I'm going to do this as a separate step so that if you go back and look at these notes, you can see what I'm doing. So I wrote out the pattern first. A squared plus 2ab plus b squared. And then what am I going to do? I'm going to take that pattern and I'm going to plop in the 10 in there, where it goes in the first two sets of parentheses, and then the 3 square root of 7 in the second set of parentheses, second two sets, like that. And then go ahead and do the arithmetic from there. So you get 100 plus, and then the 2 times 10 is 20, times 3 is 60, times the square root is 7. Plus, and then this last one, that's 3 times the square root of 7 squared. Well, that's 3 squared and the square root is 7 squared. You're squaring each factor. Since it's multiplication, you're just squaring each factor. And so that's a 9 and a square root of 7 squared. That's the square root of Bob squared. That's 7. So you get 100 plus 60 times the square root of 7 plus 63. And then finally collect like terms. You get 163 plus 60 times the square root of 7. And so you've got to multiply it out like that. All right, so this pattern that I've got highlighted and boxed at the top is super helpful when you're squaring an addition or subtraction problem, especially an addition or subtraction problem where there is a square root in at least one of the terms. Right? So very helpful to know that pattern. All right, finally, one last type of multiplication that we want to look at. So let's say we have, and this is problem number 294 in your textbook, problem number 294. You have 4 plus the square root of 2 times 4 minus the square root of 2. All right, this is definitely not squaring an addition or subtraction problem because these are not the same problem. One's an addition problem and one's a subtraction problem. And this is what we've talked about before when we did factoring. This is multiplying what we call conjugates together. And remember, multiplying conjugates is when you have this situation, a plus b times a minus b. Those are what we call in algebra conjugate expressions. It's the exact same binomial, but one of them's addition and one of them's subtraction. And that's just the difference of squares, right, from factoring. And so what is it? It's a squared minus b squared. Once again, there's a pattern to this kind of multiplication. And so what do you do when you see this? Especially when you have square roots, it's helpful just to write out the pattern. A squared minus b squared. And then just plop in the a and the b. Right? So I put in a 4 here and a square root of 2 here. So that's just 4 squared minus the square root of 2 squared. And so you get 16 minus, and then the square root of 2 squared is the square root of Bob squared. So that's just 2. And so you end up with 14. Notice you don't even end up with a radical in your answer there, which is actually important. But all right, so multiplying conjugates, right? This pattern gives you the way to multiply conjugates together, right? It kind of gives you a technique for doing that when you've got 2 conjugate expressions, right? In this case, with 2 conjugate expressions, write it out as a square minus a square. All right, and it doesn't matter how complicated the expression is when you do that. So if we have 3 times the square root of x plus the square root of y times 3 times the square root of x minus the square root of y, all right? Those are conjugates. Right? These are conjugates. A plus b times a minus b. And so when you see conjugate expressions like that, you know that the pattern for multiplying these is that it's just a square minus a square. And so when you multiply this out, you just drop in those squares into the 2 sets of parentheses. So this is 3 square root of x squared, and this is the square root of y squared, like this. And so 3 squared is 9. The square root of x squared is the square root of Bob squared. That's x. And then the square root of y squared is y. And so you end up with 9x minus y to be the final expression when you multiply those together. So notice, by the way, when you've multiplied conjugates together, the answer doesn't have any square roots in it. In both of those problems, you didn't have a square root, and that's actually true always when you multiply conjugates of expressions like this together. That's something that's going to actually help us later. All right, so that's a kind of an overview of multiplication, and I've done a ton of problems so far. That's kind of an overview of multiplying two square roots together. So now let's move on to section 9.5 and let's look at division. Now division is going to bring up some issues for us that we have not seen before. So this is section 9.5. This is division. And so we want to look at some division problems and see how this works out, how square roots and division kind of relate to each other. So this is problem number 318. Problem 318. We're going to start off with some relatively straightforward problems, but we need to look at several situations here to finish up class today. So this one's just the square root of 50 divided by 10. Now notice the 10 is not underneath the radical, so I cannot divide these like they are because one's a radical and one's not a radical. So like they are, I can't divide. So the only thing I can do here is simplify the square root of 50. So the only thing that can be done is simplify the square root of 50. Because I can't divide them because one of them is a radical and the other one's not a radical. So the square root of 50 I break up as the square root of 25 times the square root of 2. I'm hoping you're getting the hang of that kind of simplification. And so the square root of 25 is 5. By the way, on my college algebra exam, the first college algebra exam this semester, a lot of problems where there were square roots that the student did not simplify or did not simplify it correctly. And so there was a lot of people losing a point here or there throughout the test because they were having trouble simplifying square roots because they came up in a lot of different places. We were talking about solving different kinds of equations, and lots of times square roots come up when you're solving different kinds of equations, especially quadratics. So you have 5 times the square root of 2 divided by 10. Now, the 5 and the 10 I can divide out because those are both factors, and so there's a common factor there of 5. So I can divide that 5 out. That leaves me with the 2 in the denominator, and so that's okay to do. And so this leaves you with the square root of 2 divided by 2. And so that would be the simplified expression at the end for a problem like that. All right, number 322 is really different kind of radical expression, square root expression that has a fraction in it, right, division. You have 3 plus the square root of 27 divided by 9. Now this kind of expression is really good to look at because as algebra students we're going to be confronted with solving quadratic equations that are not factorable, and you use square roots to do that lots of times. And so you end up frequently with answers like this one right here for quadratics, and you have to know how to simplify the fraction. You cannot divide out the 3's here, the 3 and the 9. No. Right? Because what you're doing there is you're canceling out part of a term. Right, you're violating order of operations when you do that kind of thing. Because the division is a grouping symbol, right? You're taking something out from within the grouping symbol like that. You can't do that, right? Not allowed to do that. So don't do that. That's one thing. So what do you do? Well, the only thing I can do is, at this point, at least, is simplify the square root of 27. So the square root of 27 we know breaks up as the square root of 9 times the square root of 3. And so you have 3 plus 3 times the square root of 3 over 9. All right, now there is something you can do. Because the 3 in the numerator is common, I could actually factor out that 3 out of the numerator since there's a 3 in both terms. And when I take the 3 out, I'm left with a 1 in the first term. Don't forget that 1. You can't just ignore the first term anymore, right? Using the distributive property, that 1 has to be there, plus the square root of 3. And then that's divided by 9. And see, now this is legal to do. Now you can divide the 3 and the 9 out because the 3 is now a factor in the numerator. And so I can divide that out, and you get a 3 down there in the denominator. And so the final answer here is 1 plus the square root of 3 divided by 3. Now the key here is that if there's a common factor in all 3 parts, right? So notice there was a 3 that was common in all 3 parts here, then you can divide it out. 3 is, whoops, common to all 3 parts of the fraction. And because that's true, that's a situation where you can divide it out. Right? So this is the way to look at this. So like let's say you have 2 plus 5 times the square root of 10 divided by, let's say, 10. Now, there's a 2 that's common between the 2 and the 10, but I can't do that, right? There's a 5 that's common between the 5 and the 10. I can't do that. Is there a factor common to all 3 parts? No. So no factors common to all 3 parts of the fraction. So cannot be simplified further, right? Nothing you can do there. But if you have something that's common to all 3 parts, so let's say I have 15 plus 5 times the square root of 10 over 10. So now do you see how there's a common 5 in all 3 parts? So now you can divide it out. And the 5 would divide out, leave you with a 3 there, a 1 there, and a 2 there. Now it's legal to do because you would be able to factor out the 5 out of the numerator. And so you get 3 plus the square root of 10, 1 times the square root of 10, divided by 2. Right, so if it's common to all 3 parts, then it is legal to divide it out. All right, so the last thing we want to talk about, and it's going to take us a little bit to get through this, is what we call rationalizing denominators. Rationalizing denominators. And this is the deal here. If you've got 2 over the square root of 3, something like that. The square root of 3 is an irrational number. If we look at the decimal for the square root of 3, the square root of 3, let me see, let me actually write out the decimal for this. The square root of 3 is 1.73205080756887, like that. And what happens? It doesn't terminate. This decimal goes on forever, right? And it never repeats, it never ends. Irrational numbers have decimal representations like that. It's non-repeating, non-terminating decimal. Non-repeating, non-terminating. Those are characteristics of what we call an irrational number. Another characteristic of an irrational number is that it's a number that cannot be expressed as a fraction. There is no way to express it as a fraction. When I say a fraction, I'm talking about like 2/3 or 5/3 or something like that. There's no way to do that. So like pi is an example of an irrational number, right? Pi is 3.14 159, right? 265 358,979, like that. But its decimal does not terminate, right? When you use 22/7, some of you might have used 22/7. For example, in high school, this is just an approximation. It is not pi, right? Pi is actually a number whose decimal does not terminate, does not repeat. There is no way to write pi as a fraction. It's not possible to do. It's a characteristic of an irrational number. And rational numbers are numbers that can be written as fractions. They're numbers that do repeat their decimals or they do terminate, one or the other, right? The decimals either repeat or they terminate. Those are examples of rational numbers. So like in my fraction, the 2 in the numerator is a rational number. Now for various reasons, there are situations where you don't want an irrational number in the denominator. It's not that there's something inherently wrong with it, by the way. It's just that it can be an advantage to write it so that there is no square root in the denominator of the fraction. And so what is nice to be able to do is it's nice to be able to take a fraction like this and rewrite so there is no square root in the denominator. Right, that process is called rationalizing the denominator. That's what rationalizing the denominator means, is taking a fraction that has a square root in the denominator, like the square root of 3 in this case, and rewriting the fraction somehow so that it is written in a form where the square root of 3 is not in the denominator, where there's no square root in the denominator at all. And sometimes this is really easy to do, and sometimes it's not so easy to do. And so that's what we want to look at to finish class today, is actually looking at problems where we're rationalizing the denominator. That's a skill that you need to be able to do in college algebra in various different places and in classes beyond also. This rationalizing process takes a fraction and makes it look different, and sometimes the way you make it look is just an advantage for various reasons to write it that new way. All right, so in a problem like this where there's just a single term in the denominator, this is actually an easy process. There's just a single term in the denominator. And when that happens, when you just have a single term in the denominator, remember you have this equivalent fractions property that allows you to take a fraction and write it so it looks different, right? So where you're multiplying, it's legal to multiply the numerator and the denominator by the same thing. So in this case, all you simply do is you multiply numerator and denominator by the square root of 3. Square root of 3 over the square root of 3 is legal to do. You're not changing the value of the fraction when you do that, because this is just equal to 1. This is what we call the equivalent fractions property, remember. So this is always legal to do. So in the numerator, you get 2 times the square root of 3. I can't multiply those together. But look what happens in the denominator. And that's why this works. The square root of 3 times the square root of 3. And that's another example of our square root of Bob times square root of Bob. And what happens when you multiply the square root of Bob times the square root of Bob is if Bob is positive, you get Bob. Right? And so this is just 3 down here. And technically the square root of 9, but that's 3. And this is a rationalized version, what I'm putting in the box right here, of the first fraction. They have the exact same value, but the second one does not have a radical in the denominator. And notice I'm definitely not using the word simplify here, because the new expression is probably more complicated than the first one. All it is rationalized, right? And so if you check your answers in the back of the book, typically the answers in the back of the book in an algebra book are going to be rationalized. They're usually not going to be left with a radical in the denominator. All right, so that's our first example. So second example, let's say we have the square root of 3/7, the square root of 3/7. Well, this one is a problem that we're rationalizing could help here, or could make it look different, because this is technically the square root of 3 over the square root of 7. And so there is a square root in the denominator. And so what do? We, with a single term, all we have to do is just multiply that denominator, that radical in the denominator, by itself. So we just multiply the top and the bottom by the square root of 7 over the square root of 7. And then multiply what you've got left. So square root of 3 times the square root of 7 in the numerator is the square root of 21. And in the denominator, the square root of 7 times the square root of 7. That's the square root of Bob times the square root of Bob right there. And so that gives us Bob. That's just 7 right there. And so that would be the rationalized version of the first fraction. All right, so here's what we started with. Square root of 21 divided by 7 is the rationalized version of it. Okay, so that doesn't look too bad. Let's look at another problem. Let's say we have 6 over 3 times the square root of 10. And let's not make that a 3 right there. Let's make that a 5. Like that. Okay, so 6 over 5 times the square root of 10. Now the 5 we don't care about, because the 5 is not underneath the radical. So there is still just a single term in the denominator. There's no addition or subtraction. So all we do is, to rationalize here, is we multiply by the square root of 10 and the square root of 10. Right? We don't care about the 5 at all. So in the denominator, you get 5 times, and there's the square root of 10 times the square root of 10, which is 10. And in the numerator, I get 6 times the square root of 10. And so this would be 6 times the square root of 10 over 50. And then remember, you always simplify a fraction when you can, and there is a common factor here of 2. And the 2 divides out and leaves you with a 3 and a 25. And so this would be, to finish, would be 3 times the square root of 10 over 25. And that would be the kind of the simplified, rationalized version of the first fraction. Notice they don't really look anything alike, and you might have a suspicion that they're not the same number, because they really don't look a lot alike there at all. But they are definitely represent the same number. If I got a calculator out and got a decimal approximation for those two, I would see that the decimal approximations are the same approximation, basically. All right, let's say we have something like this. We have the square root of 7 over the square root of, well, square root of 7, sorry, over the square root of 40. Now, you could rationalize first here if you wanted to, and do that right away, but the numbers get a little bit big, and so what I would do here first is that radical in the denominator simplifies. So simplify this radical first. Then rationalize at the end, because it makes the numbers smaller. So I think that's a good strategy to use there. So simplifying means take the square root of 40 and write it as the square root of 4 times the square root of 10. So this would be the square root of 7 over 2 times the square root of 10. Now go ahead and rationalize that. And so you multiply the top and the bottom by the square root of 10. Like that. Right, and then when you've done that, you end up with the square root of 70 in the numerator. And then in the denominator, you go 2 times the square root of 10 times the square root of 10 is 10. And so you have the square root of 70 over 20. One of those is a square root, the other one's not. There's absolutely nothing you can do with that. The square root of 70, believe it or not, does not simplify. The only factors of 70, so factors of 70 are 1 and 70, 2 and 35, and 7 and 10, and let's see, 5 and 14. None of those are perfect squares, right? There's no perfect squares there, and so there's no way that it simplifies. And so you're stuck with it just like that. So there's our simplified, rationalized version of the first fraction. Right. All right, so finish the day with 1 or 2 problems. What if there is addition or subtraction in the denominator? And so what if there is addition or subtraction in the denominator? Put a question mark there. So this is what I'm talking about. Let's say we had 3 over 5 plus the square root of 6. And so you see what I'm talking about is that there is addition in the denominator here. And this is where let me flip the screen back. This is where the stuff we were talking about on this screen, where we're multiplying conjugates together, is going to be a benefit to us, because notice in both of these problems we were multiplying conjugates, and the answer we were left with did not have any square roots in it. Right? So when you multiply conjugates of square root expressions, no square roots are left. And so notice that's what I've got here, is I've got a square root in the denominator. If I could multiply by the conjugate of this expression in the denominator, then I'm not going to be left with any square roots in the denominator. But what do I have to remember to do? I have to remember to multiply the numerator by the same thing, right? And so we multiply numerator and denominator by the conjugate of the denominator. So let me write that underneath it. Multiply numerator and the denominator. Remember, you have to do both. By the conjugate of the denominator. Let's go ahead and highlight that. All right, that's the answer to that question as far as rationalizing goes. And when I say that question, I'm talking about this question right here. All right, what if you have addition or subtraction in the denominator and you're trying to rationalize? What do you do? And the answer there is you multiply numerator and denominator by the conjugate of the denominator. All right, so let's see, what do we get? In the numerator, just leave it as 3 times 5 minus the square root of 6, because it might simplify at the end, so I leave it as multiplication. In the denominator, remember how conjugates multiply. It's a square minus a square. And in this case, it would be 5 squared and the square root of 6 squared. Right, and so in the numerator, you just have 3 times 5 minus the square root of 6. In the denominator, you get 25 minus, and then the square root of 6 squared, that's the square root of Bob squared, is 6. And so you have 3 times 5 minus the square root of 6 over 19. And sure enough, you've rationalized the denominator. And so that thing I just put in the box is the rationalized version of that first fraction. And you can see very clearly why I do not call this simplifying, because you sure as heck aren't simplifying that expression. It's not any simpler than the original one. In fact, it's decently more complicated. All we've done is rationalized it. Right? We've rewritten it so that there's no square root in the denominator. All right, we'll finish this with one last problem, and then this will be it for the day right here. Yay, and this will be it for the week. So this is problem number 370 on 1072, so page 1072, number 370. So you have the square root of 7 over the square root of y plus the square root of 3. So again, the denominator has an addition problem in it, right? And so that's the key to when you would be using conjugates, is if the denominator has addition or subtraction. It could be either one, but either one of those you're going to use conjugates to rationalize. All right, so the conjugate of the denominator in this case is the square root of y minus the square root of 3. And so I'm going to multiply the numerator and the denominator by that quantity. All right, so let's see what happens here. We get, first of all, in the numerator, I'm just going to leave this as the square root of 7 times the square root of y minus the square root of 3 at first. So let's just see what happens. In the denominator, I've got conjugates. So I know that's a square minus a square. And then you just drop in those numbers. So this is the square root of y and the square root of 3. Right, it's a squared minus b squared. And so you get the square root of 7 times the square root of y minus the square root of 3. And then in the denominator, this is the square root of Bob squared in both cases. And so this is just y minus 3. Now in the numerator, I mean, there's nothing I can simplify or cancel out or reduce here. So you could use the distributive property in the numerator if you wanted to and get the square root of 7y minus the square root of 21. Now I would not care personally which way you wrote it at the end. And as you've seen before, WebAssign can sometimes be pickier than me. And so WebAssign might count one of those right and one of those wrong. I just don't know. That's a good question. But those are both certainly good versions for the rationalized version of this fraction right here. All right, so practice problems from the textbook. If you are looking for good practice problems, really on page 1071, really any problem from 317, the author actually kind of goes nuts with some of these, to be honest with you. So 317 through 327, and then 339 through 371, and then 379. So all of those would be good practice problems. And again, I don't know if any of you work on these or not, but these are great practice problems for these kinds of things we've been talking about. So any practice you do there is going to be helpful. And then on page 1056, I would look at probably problems 233, anything from 233 through 299 would be helpful. These are all great practice problems. Certainly nothing I'm ever going to pick up, but not a bad place to look at practice problems at all. Okay, so any of you who are with me online, you guys have been very quiet today. Anybody have any questions at all?
Not right now.